All right, we are going to combine together 4.5 and 4.6 into multiple different lessons. So we're not just doing all of 4.5 and all of 4.6. I put them together in a way that, for me, makes the most sense so that you can understand the relationship between the information. So I'm going to do a quick intro on what 4.5 and 4.6 are on, and then the lessons following this, I'll go through different example types to explain it even further. So these two lessons go over two theorems. One of the theorems here is the irrational conjugates theorem. The other one is the complex conjugates theorem. So they're extremely similar to each other. Really the only difference is one uses irrational numbers, like the square root of 5. And the other one uses complex numbers, which means it has your imaginary I in it. So, definition-wise, the irrational conjugates theorem says if a polynomial has a factor of a plus the square root of b, then that polynomial also has a factor of a minus the square root of b. So this comes from a truth of the quadratic formula. So if you simplify the quadratic formula all the way down and you get something like this, 2 plus or minus the square root of 5. What does that represent? Well, it represents two different values. That's what that plus and that minus means. It represents 2 plus root 5. And it represents 2 minus root 5, which is why we have the irrational conjugates theorem. If you have the addition of an irrational, you always have the subtraction of that irrational as a factor also. The other theorem is the complex conjugates theorem, so extremely similar. It says that if a polynomial has a factor of a plus bi, I being our imaginary numbers, then it also has a factor of a minus bi. Again, that comes from the exact same piece of our quadratic formula. So if I had 2 plus or minus the square root of negative 4, we need to think about how we rationalize negative roots. They are not real, they are imaginary. So if I have 2 plus or minus the square root of negative 4, well, 4 actually has a root, it has a square root of 2. So I can simplify this answer to 2 plus or minus 2i. So it's 4, the square root of 4 is 2. But it's a negative 4, so I need to represent it with that I, that imaginary I. Again, this represents two different zeros. This represents a 0 at 2 plus 2i, and it represents a 0 at 2 minus 2i. So following that complex conjugates theorem. All right, and then again, like I said, this all comes from our imaginary I. You need to remember throughout this whole process that if you see the square root of a negative number, we can remove or rationalize that negative with an I. And if you ever come up against an I squared holds a set value of the number negative 1. So we'll use that a little later on. All right, so let's talk about some prior knowledge that we're going to need to remember and utilize, and then we're just adding the complexity of irrational and complex numbers into something we already know how to do. So let's talk about some prior knowledge. If I was to ask you to write a polynomial function in factored form, and I give you this function here, f of x equals 5x squared minus 5x minus 30. So that is a function. Right now it's in standard form. My goal is to get it into factored form. The first thing you always ask yourself is there a greatest common factor that you can divide or factor out of each of those terms. I see a 5, and a 30, all numbers divisible by 5. So I actually do have a greatest common factor of 5. If I divide 5 out of each of those terms, I'm left with x squared minus x minus 6. I keep my 5 on the outside because I want factored form, so I want an identical truthful equation that represents that exact same formula. I'm just writing it a different way. So I'm not reducing it, I'm factoring. So I'm showing each of the factors. One factor being the value 5. Then I look and I see, oh, I have a quadratic here. How can I deal with this quadratic? Whenever you get to a quadratic, you need to ask yourself 2 questions. Is there a value that adds to your b value? And those 2 values need to multiply to your c. So, are there 2 numbers that add to -1, multiply to -6? So the factors of 6 are 1 and 6, 2 and 3. And if you have -3 plus 2, you're given -1. And if you have -3 times 2, it gets you a -6. So my factors are x minus 3 and x plus 2. So this is the exact same function, just broken apart and rewritten in factored form. If I distributed that, it would get me all the way back to the exact function I began with. So I didn't reduce anything out, I factored, I divided and broke apart different pieces. Number 2 is asking us to use factors, so it's already broken apart for us, and we need to put it into standard form. So there's a special name. When we have sets in parentheses that are multiplying with one another, there's a unique way to multiply those terms with each other. Do you know what that name is? It's called distributing. So we are going to distribute. When you distribute, you can only distribute 2 parentheses with each other at a time. So you cannot distribute all 3 sets that you're given right now together. You can only do 2 sets at a time. So let's start with the first 2. So we're going to do x times x. So again, we're not changing it, we're keeping the exact same function. So x times x is x squared. X times 4 is plus 4x. -3 times x is -3x. -3 times 4 minus 12. Now I had 2 sets of parentheses. When you distribute, you don't get rid of both of them. You actually only get rid of 1 set. And we have not utilized that. So we need to make sure that we don't forget about it. Right, can you simplify that down? What do you see that we can simplify? Those middle 2 terms. So I have x squared plus, so I have 4x minus 3x, so I only have 1x left, minus 12, still multiplying with our last term that we have not distributed into. Okay, so I have 2 sets of parentheses now, so I can distribute those with one another. So you continue to distribute until all sets have combined together. So we're going to distribute again. Alright, so x squared times x. Alright, so this is still f of x. I'm not doing a new function, same function. X squared times x, x cubed, x squared minus times -5. So minus 5x squared. I'm going to take this x now. Oops. X times x. So plus x squared, x times -5, so minus 5x. Now I need to take that -12. negative 12 times x, so minus 12x, and negative 12 times negative 5, I get positive 60. I always double check to see if you can simplify. So I'm going to simplify that. So my parentheses, this is all now one set. So I can simplify. So some x squares I can combine and some x's that I can combine. So my function, the exact same function that we started with, but written now in standard form, is x cubed minus 4x squared minus 17x plus 60. You'll see a pattern throughout this chapter that if you have 3 factors, you should have x cubed as your first term. If you have 8 factors, you should have x to the power of 8 as your first term. That greatest degree tells you the number of factors in a fully factored form. All right, so if you keep going through the next lessons, we'll start diving into the specifics about how you take this and do that same process when you have irrationals or complex numbers mixed in to your factoring or distributing to standard form process.